Hello, welcome everybody to our Integrability Journal Club. And this week we are very happy to have Roberto Tateo from the University of Torino. And he will tell us about the TTbar deformation and a promising 4D generalization. Please, Roberto.
Hi, everybody. First of all, I should thank the organizer of this journal club for the kind invitation to speak here. Essentially, I will talk about a spatial deformation, a spatially relevant deformation of two-dimensional quantum and classical field theory, which is this deformation is called TTbar deformation. It is actually related to the determinant of the stress energy tensor, not only the holomorphic and anti-holomorphic part of the stress energy tensor in a conformal field theory. And then in the second part of the talk, I will try to generalize to some idea, some geometric idea about the TTbar deformation to 4 dimensions. So I will propose a generalization, but unfortunately only a classical level of the TTbar deformation in 4 dimensions. So this is now becoming a quite long story. So and I'm collaborating on this topic with many people, and especially master students from Torino. So this is so nowadays, I mean, let's say starting from 2016 till now, there are.
Scrivo, guarda che non hai dato quello, ti risponde, ti chiede un'informazione, cioè moltiplicatelo, è vero che posso.
Okay. Yes. Okay. So since 2016, essentially there has been uploaded on the archive something like 200 papers on the subject. So it turns out that the subject is particularly interesting because it's interdisciplinary. So there are people working on integrable models as I and my collaborators. And there are applications in string theory, in effective string theory, like describing the quark-anti-quark confinement or the property of the quark-anti-quark flux tube in arbitrary dimensions, and relation with the ADS-CFT, etc., etc. So the last 3 papers here, the one by Cardi, Tolley, and Dubowski et al., are giving us the main motivation for the generalization to the TTbar theory to 4 dimensions. Okay, so the main motivation are the following, are the standard one. So everything started actually a few years ago, and my attention was attracted by a paper by Dubowski, Flauger, and Gorbenko, where they modified the thermodynamic Bethe-Ansatz equation for the free fermion, for the free boson, and in a simple way by introducing modification of the scattering matrix, which is a trigger for free boson. So introducing what we call a Cdd factor, and they were able to get out of this massless free fermion theory the spectrum of the Nambu-Goto theory in an arbitrary dimensions. So essentially my attention was attracted by that paper because I like TBA equation, and we essentially had the first paper with Davide, Nando Liozzi, and Michele Caselle on the extension of this result at the arbitrary conformal field theory and on a strip. So a situation which is more, closer to the standard study of the flux tube in gauge theory, in confining gauge theory. But there are, okay, now I think people is not working anymore or much about this connection with effective field theory, but is more interested on general issues related to perturbation of field theory by irrelevant operators. So, for example, we are interested in the understanding the emergence of a singularity in the RG flow, like the Landau pole singularity, or square root or branch point singularity in the thermodynamic Bethe-Ansatz flow, so in the finite size correction for the energies. So everything it fit all together, because there is also a relationship between this irrelevant perturbation and this ambiguity, CDD ambiguity in the exact S matrix approach to integrability. So for many years, let's say when I was younger, people working on integrable model, they always saw that you should start from a well-defined ultraviolet fixed point, so which was our initial conformal field theory, and then perturb it with a relevant operator, so which would drive you away from this ultraviolet fixed point. In this way, you can reach you would flow toward the infrared. That could be a trivial theory or another conformal field theory. So at the beginning, all the theory we studied were massive theory, but then Alyosha Zamolodchikov many years ago managed to generalize this approach, in particular S-matrix approach and the thermodynamic Bethe-Ansatz approach, to describe flow between two non-trivial fixed points. So a well-defined conformal field theory in the ultraviolet and a well-defined non-trivial quantum field theory in the infrared. And the typical example is this flow connecting the tricritical Ising model to the Ising model. As I said many times in my talks, so then at this stage we start to try to understand the behavior of these models close to the infrared, and in particular try to detect what the leading and which were the leading and the subleading attracting operator in the infrared. And at that point, it was at that point that the TTbar operator emerged as just the product of T times T bar in the conformal, exactly at the conformal point. The next step then is try to use this information to somehow flow back, so shoot back from the infrared into the ultraviolet, and we know this is essentially our level of knowledge that this is essentially impossible. And also, but it is now clear that if you try to flow back, maybe you can define, you know, from physical point of view, a good flow, but you might not find anything standard in the sense of a conformal field theory in the ultraviolet. It might be a non-local theory, so something much more complicated. So if you have in your hand a classical system or a classical Lagrangian, so a classical model, and you think that the theory is actually integrable also both at classical and the quantum level, then we usually try to bypass the problem of brute force quantization of the theory, assuming again integrability. So we immediately look for the exactest matrix of the theory, and since we assume that the theory is integrable, the exactest matrix should be factorizable. So it means that the n-body S matrix would factorize in the product of two-body S matrices, and the two-body S matrices should fulfill the Yang-Baxter equation. So the usual starting point at quantum level is not a brute force quantization, but goes through the imposing of the Yang-Baxter equation with the right symmetry. And then you have to solve this equation together with the unitarity and cross symmetry constraint. Okay, If you're lucky, you can find the solution, and then essentially out of the scattering matrix, you can try to build up a correlation function, at least asymptotic perturbative expansions, or try to calculate exact quantity like the final size correction for the energy levels. However, it is well known that there are phase factors that fulfill trivially both the Yang-Baxter equation and the Crossi unitarity equation. So there is an ambiguity, and once you have the S matrix, you really need some other tool to check that really it is the S matrix of your initial theory. And this method, it's essentially one of the methods we know. It's probably the only one. It's called the thermodynamic Bethe-Ansatz, which allow you to describe your field theory on an infinite cylinder of circumference, let's say R, and you can vary the circumference of the cylinder and describe and move from the infrared into the ultraviolet and vice versa. Okay. So we also know, so this CDD ambiguity is also a bit puzzling, because we know that in some cases you add this CDD factor, this phase ambiguity, and if you plug it in the thermodynamic Bethe-Ansatz equation, you get something which goes wrong in the ultraviolet. So you encounter some singularity before reaching the ultraviolet. On the other hand, we also know theories that possess the same mass spectrum, but differ by CDD factor. So the central charge is different. The simple example is the Sanch-Gordon model, where the S matrix is essentially a CDD factor. And so it has the same S matrix up to a CDD factor of a free fermion theory, like a Majorana fermion theory. But we know about the theory which are more complicated. For example, a affine Toda field theory, for example, E8 affine Toda field theory, has the same mass spectrum as the Ising model perturbed by a magnetic field. So it will be nice to give an interpretation to this CDD factor, and what is emerging from here is that the CDD factor are actually related to irrelevant perturbation, and maybe an infinite number of irrelevant perturbation. Okay, but let's concentrate on the simplest CDD factor we can think of, and this it's related to this phase factor here, which
could I ask? Sorry, Roberto, is it in some sense complete set of irrelevant deformations, or is it like a big subclass?
Well, that we don't know, but it's related to to the set of conserved currents of your theory. So if you don't want to spoil integrability, so it's not so general. So well, it's quite general, but if you want, since you have an S matrix and a graph matrix, so you remain in the domain of integrability. So it's not a generic irrelevant operator. You might have an irrelevant operator which is breaking anyway integrability.
But as long as you want this, basically is just periodicity, right? That lets you write the most general deformation as sinh and theta, if you sum over all of them.
Yes. So you mean that there is a huge ambiguity anyway, is it?
Well, another thing is that if you really have an infinite series, then it's not obvious to me that it's still irrelevant. I mean, a sum of irrelevant terms is clearly relevant, but once you start taking infinite sums, I guess anything could come out.
Yeah, I agree. Okay, but yeah, I think it's a setup that in general we don't fully understand. So for example, we don't understand whether it is possible to move from a free fermion, Majorana free fermion, to the Sainz-Gordon model just by adding systematically irrelevant operator to the theory. So you probably can do that, but I think nobody really investigated that. Okay, so this is the simplest Cdd factor you can think of. It contains a parameter, which I will in the following call tau, and it's proportional. The phase here, the scattering phase, is proportional to the hyperbolic sign of the difference between the two, the rapidity of the two particles. So this Cdd factor is it's quite interesting. It's very simple, first of all, and for tau greater than 0, actually the S matrix is well, if this is bounded in the physical strip, this is also this term is bounded in the physical strip. So it seems to be a reasonable Cdd factor. You can modification of your S matrix you can put in, or you can consider. But if you go to tau negative, then the S matrix is unbounded in the physical strip, and this usually means that the theory is you lose causality, macro causality from the beginning. So people is always thinking about this positive tau as a good sign of the perturbation, this negative tau as a bad sign of the perturbation. Still, in both cases, you have some problem in the ultraviolet, and we will discuss about this. So people is thinking that in the ultraviolet, the theory is non-local anyway. Okay, so one of the reasons we actually discard in the past the Cdd factor is that it actually growing. So in the at high energy is not going to a constant, this phase factor. So it means that again, it signals that again that the ultraviolet it's somehow problematic. So this is why for many here we actually ignore this possibility. But let's go ahead and try to use this Cdd factor, so this one, into the standard equation describing the finite size behavior of the energy level, for example, of the Sainz-Gordon model, which are well studied and well known integrable theory. So the approach to study finite size, the finite size property of the energy level. So essentially, you are thinking about putting your quantum field theory on an infinite cylinder of circumference r, which is this number here, and then usually starting from the exact S matrix, you can derive a set of equations which we call thermodynamic Bethe-Ansatz equation because they have a thermodynamic origin. And Zamolodchikov explained us how duality essentially determine the exact spectrum of the exact finite size spectrum of the model. This, for the Sainz-Gordon model, there is an alternative equation, which is simply, is often called the de Vega equation, but it was derived 1 year or 2 years before by Klumper, Batchelor, and Pierce. It's more compact compared to the thermodynamic Bethe-Ansatz because it's a unique, it doesn't change as you vary the parameter in the Sainz-Gordon model. So the coupling in the Sainz-Gordon model, the equation remains the same, while if you want to use the alternative equation, thermodynamic Bethe-Ansatz equation, then you have to fix the coupling beta, and then as you move the coupling, you have to change the thermodynamic Bethe-Ansatz equation. So it's more complicated, and this is really much more compact. So you don't have to know everything about this. I'll explain what's the origin of the various bits. So this f here is the unknown function, so the solution you want to find. and it's called counting function, and it appears here on the left and here in the convolution term on the right. The first term here, we usually call it a driving term, and this contains the volume, so this circumference of your cylinder, the mass, this is the mass of the soliton, and the bare momentum of the particle, which is sine of theta if parameterized in terms of the rapidity. And then if the theory was a free theory, then you wouldn't have this term here, but due to the interaction, the momentum is dressed in some way, due to the presence of these other two terms, which are related to the S matrix. So the kernel here, in the convolution here, is simply the logarithmic derivative, apart from this factor here, of the soliton-soliton S matrix. Okay, and the contour here of integration, C1 and C2, they run just above and below the real axis for the ground state. For excited state, the equation has a similar form, and this was done by Fioravanti, Ravanini, and other people. You have to introduce extra term here in the driving terms, which essentially come from picking up a residue in the complex plane. Okay, so you can think about adding extra term here, or just by deforming the contour here, C1 and 2, they move, so they are more complicated, so they can pick up a residue terms. So suppose now you have solved this equation here, so you know the counting function, then you use these two pair of equations to reconstruct the energy and the momentum of the system. And since we are with periodic boundary condition, the momentum is quantized, while the energy is in general very complicated, apart from in the particular limit of UV and infrared. Okay,
sorry, what is alpha?
Alpha, it's called quasi-momentum. It's related to the fact that the Sine-Gordon model has an infinite number of minima. So it's like related to block wave function. You know, it's called quasi-momentum. You can think about it as also as a twist, like some twist boundary condition. Okay. Now let's, so the S matrix only appear here in the kernel, so we can now include into the kernel the Cdd factor. Okay, so we now simply modify the kernel by adding this extra term, which depends on the parameter tau, and the derivative of sine is cosh. So this is the extra term you have to include, and you put it in the kernel. And actually what you get, after you do the calculation, it's a simple redefinition of the driving term, a simple change in the driving term. And and here it comes the surprise. So first of all, you see that this is R is the volume of your system is now changed. So you get an extra term, which is proportional to the energy, the total energy of your state. And then there is an extra term which vanishes for P equals 0, so for total momentum equals 0. So it's a simple modification, only of formal modification, only of the driving terms of this bit here. And somehow it's also strange because it is like you change the volume of your system with something which is proportional to the energy of your state. Okay, so including this Cdd factor, essentially we didn't change, we didn't spoil Lorentz or translational invariance. So essentially the momentum you can prove. It's very easy to prove, that simple to prove that the momentum still remain quantized as for the under formal theory in the standard way. Now, the trick to manipulate this, to proceed or to manipulate this is to write the driving term, parameterize the driving term here in terms of R0. So a new volume, which we call R0, and a shift in the rapidity, which we call θ0. Okay, so this is just a parameterization, and to fix θ0 and R0, you have to match this deformed driving term here. Okay, so essentially the match consists in this set of equation, which would fix θ0 and R0 in terms of P, E, tau, etc., and R. Okay, but once you do that, so it's a non-trivial redefinition, but once you do that, you notice that the counting function f at R, volume R, and tau different from 0 is actually equal to the counting function at tau equals 0, but with a redefinition of the volume R0 and a shift in theta. Okay, so now it just means that if you know the original counting function, do with this change of variable and define in R0, etc., you in principle can fix, you also know the counting function for the deformed model. Now you plug this property, use this property inside the definition of the energy momentum, and you discover that there is this relation between the energy of the perturbed theory and the energy and momentum of the unperturbed theory. So again, with that redefinition of the circumference of the ring. Okay, so this looks like a Lorentz transformation, but somehow in θ0, due to this equation, there is θ0 depends on trivially on tau, on E, and R, etc., etc. So this is a non-trivial equation. Still, it implies that you have this property. So E square at tau minus P square is equal E square at R0 at tau equals 0 minus P square now at R0. Okay. Now,
could I ask? So you said P is quantized still, right?
Yeah, still it is quantized, but now is quantized like a constant divided by R. And now in this expression here, it appears P at R0, and R0 is, is moving with tau. So R0.
If I look on the cosh of theta, right? So in the right-hand side, then R, the usual R is fixed, right? For you, is a parameter. Tau is also a parameter.
Yes.
And P is quantized. So actually, theta is kind of a fixed quantity, right? For all states, you fix it once and
yeah.
So it is like a boost.
It is like a boost, but it's θ0 is not, is not arbitrary because it's related, it's constrained by this equation.
But it is whatever you want. You just adjust tau, right?
Yes.
So it is arbitrary.
No, it's not arbitrary. It's just a map. You have to solve this equation to find θ0.
Yeah, so it's like our cosh of tau and then some constant.
Yeah, but
I want to solve
the equation. Here R0 is non-trivial also.
Yeah, but the second term, second equality.
Yes.
No, for sinh, but second one. Isn't it only tau which is a real?
Yeah, but P is dependent on R0, so it's quantized. So it's a number divided by R0, not divided by R. Okay, so that.
Okay, so
yeah, it's not a constant.
Here, so
it's still so theta does depend on the state.
Yes.
Still. Okay.
So so there is some mass hidden in this transformation which look like a Lorentz transformation, but still this equation hold, and there is a standard way to extract the associated flow equation. So what you fix R0 and you take derivative with respect to tau of this equation, and you use some constraint coming from here, and what you get, it's this flow equation for the energy levels. So I restore here the n. It means that this equation is true, is valid for any state in the theory. Okay, so this is quantized, so you know how to do what you get if you do the derivative with respect to r of p square. And then you have this extra constraint if you want to derive this equation, but you have to impose this extra constraint, which is actually contained in this set of equations. Okay, but this is the result, and essentially this coincides with a Burger equation with a source term which is related to the presence of this p square of r there. Okay, so it's a first order equation in the parameter tau. So it means that you just need to have an initial condition, and then you can solve and move away, so increase tau and find the exact solution at finite tau. So it's a flow equation. That you can solve. It is especially simple when you have a p equals 0. Otherwise, it's slightly more complicated, the solution. So this is.
Could I ask, just for those who only knows about burgers from McDonald's, can you like give some?
Okay. So the Burger equation is burgers or whatever. So is the simplest, so it emerged in fluidodynamics, is the simplest equation where you can see the wave breaking or branching of the waves. Okay, so essentially, if you look at this expression, let's forget about this. If you perform the derivative with respect to r, you have, you get what you get, it's e times the derivative of twice e times the derivative with respect to r of e. Okay?
It's nonlinear, Roberto, isn't it?
Yeah, it's nonlinear, and somehow it tells you that the velocity of the wave is depending on the height. So if you think about this as the height of the wave, the velocity of the wave of any point in the wave is depending on the height of the wave. So the higher is your point, the faster it would go. So it means that the lower point, so lower energy point, will flow slower than higher point. And this is the reason why you have this wave breaking phenomena. It's a bit like, surface wave on the sea forced by external wind, and the wind is stronger in the upper part, so the upper part is moving faster than the lower part. So it's this branching of shock phenomena is also called wave breaking. So it's not really breaking because everything is analytic. So it's a branching, is more a branching of the wave in our case. Okay, so let's see.
Excuse me, Roberto, I missed, I do apologize, but I missed, how did you derive this equation? Could you repeat it, please? The Burger's equation from.
Okay, I can show you later on, but or maybe in private, but it's actually a consequence of all these constraints.
Ah, you didn't say. Okay, sorry. I thought I missed it.
Out of here, usually you fix R0 to be a constant, and you derive.
Okay, sorry.
It's a standard way of treat. Okay. So there is a standard way to get out of that equation the flow equation of this type. Okay, so as I say, this is a first order differential equation in tau. So it means that you need only one initial condition, and it means that you just need the unperturbed spectrum as an input. So the TBA result, or the nonlinear integral equation result for the spectrum is always this form here. So these are the energy level for the free Majorana fermion on finite volume R. And you see this is the ground state. So it's normalized such that they go exponentially to 0 at large R, so in the infrared. So and then you have a gap, which is twice the mass of the Majorana fermion. And then you have, after the gap, you have the continuum. Okay, so these are only a few states, but there are other coming. Okay, and then when you go to R, so toward the plane, so they become dense here, and they would remain the mass gap or twice the mass gap there. So this is a general picture, and apart from different wobbling of different number of states, it's very similar to other models like the Saint-Gordon model, etc., etc. Sometimes if you have bound state, you might have level under the threshold, which correspond to the one particle state under threshold. Okay, but since this perturbation, we anticipate that this perturbation, this Cdd factor, is related to an irrelevant perturbation. We expect that the infrared behavior, so at large R, is unaffected by this Cdd factor, but something strange might happen in the closer to the ultraviolet. In particular, since we are dealing with a Bourdieu equation that exhibited this wave-breaking phenomena, so we expect the emergence of singularity close to the ultraviolet fixed point. So this is the typical behavior with a constant here, C effective, which parameterizes essentially C minus 24 delta, where delta is the dimension of the operator under consideration. And this is the typical behavior of the energy level close to R. So this is somehow universal, and it's related to the underlying conformal field theory characterizing the ultraviolet fixed point of our system. Okay, so suppose that we are considering the ground state, for example. So C effective is positive. Let's say it's equal to 1, and tau, the perturbing parameter, is also positive. So it's small here. And you see that the dashed line corresponds to the original and perturbed energy level. And now, if you increase the tau even just a little bit in the positive direction, this energy level is bending toward the physical region. What I mean, R greater than 0, volume greater than 0, in this way, is forming a branch point here. And this is the real part of the energy level. So this, in this region here, the energy is complex. Okay, and so it's branching in this way with a branch root, a square root singularity. Now, if you consider instead an excited state, so C effective is usually, as I said, C minus 24 delta. So it becomes a certain point negative. So for generic excited state, C effective is negative. And so for an excited state, again, for tau positive, the energy level is actually bending toward the physical region, which is R negative, okay, negative volume. However, there is a physical state coming from the negative volume region, which is bending toward the positive region, the physical region. And so again, as in this situation, you have a doubling of the energy level. Okay, so I think understanding the meaning of this, they are probably unphysical states. So probably you have just to ignore them, but I think this is not really fully understood. Okay, so as I said at the beginning, there is a deep relation between TTbar and string theory, and you can, the first thing that emerge are related to the study of conformal theory limit of the above described equations of the Bourdieu equation and so on. So if you are starting from a conformal field theory, then actually you can solve exactly the Bourdieu equation, and it turns out to be equivalent to this pair of algebraic equation. Okay, I'm going to explain what's the meaning of this equation. So here is E plus is the total energy of the right mover sector. Okay, so E plus has the same form as the conformal, as in the conformal limit, apart again that R, the volume, is now shifted by this amount. So 2 tau and the energy, total energy of the left mover sector. Okay, so you have now a coupling. So you have essentially with the Cdd factor, you have introduced a coupling between right and the left mover sector. Somehow you have spoiled the conformality. Okay, so now you have E plus, which is coupled with E minus, and vice versa. E minus is coupled with E plus. And again, there is some geometrical hidden property here in which everything is equivalent to changing R, the volume of your system, into R plus 2 tau E plus or E minus. Okay. Now, this is a very simple set of equations. You can solve it and calculate the total energy, which is E plus plus E minus. And this actually get this very interesting form with a square root. Okay, and here it comes the connection with string theory, because this is exactly the Nambu-Goto spectrum in the critical dimension, D equal 26, which correspond to C central charge of C equal to 24. Okay, so again, so this is really the first thing coming from this paper by Dubonsky and generalized to generic conformal field theory by us on a relation between, let's say, non-critical string, or at least a string theory, and this particular Cdd factor. Is it everything okay? Okay, so this is the first things of a connection between this Cdd factor and string theory. And now,
sorry, Roberto, you say it's connected to a non-critical string theory. How would this integrable theory know that it's a non-critical string theory? So how would it know about the dilaton and so on?
Yeah, this is again a mystery. We don't know, but this is an exact result. So somehow, so everybody would agree that for C equal 24, central charge equal, there is no problem. This is the right spectrum.
I think you meant to say critical, right, Robert?
So this is the critical, yeah, but C effective here is actually general, okay? So you flow out of the critical string theory and move to a generic string theory, let's say.
Yes, and so how would it, how would the fact that now the dilaton grows manifest itself?
Yeah, we don't know. But
I mean, in other words, is
theory.
it true to say that you don't notice this?
Yeah.
So there must be some non-perturbative string states in this theory that
I think, let's say, outside the critical dimension, we don't know exactly what's the interpretation. But you know, there are statements, for example, by Berlinde, which relate the TTbar with the non-critical strings. Anything like that, but I think this is not the main point of my talk. So I think the interpretation of this outside the critical dimension, it's still, you know, should be explored, and I didn't explore it very carefully.
Yeah, maybe
do you have a tachyon in the spectrum?
Okay, yeah, you have the square root, so you still have the branch point in the spectrum. So you still so the form is the same. So actually, from the point of view of this expression, there is no difference. So everything is moved at c equal 24. So there is or d equal 26. So everything it's is smooth. There is no and the underlying theory, it could be any conformal field theory.
Yeah. But the critical string theory has a tachyon. Do you have it in the spectrum?
No, the tachyon, I think it's related to the branch point of the square root. This is an Nambu-Goto theory, so it's the simplest string theory if you want.
Yes, but it does have a tachyon.
Yes. So it's the energy. I guess it's this this problem here, is it?
Negative mass square.
Yeah.
And by the way, like always, you could cure it by just adding fermions. If you did 8 bosons, 8 fermions, you would not have this problem.
Okay.
Sorry, why would you see the tachyon? So you are describing, can I say something?
Yes.
So you are describing long strings, right? So it's different. I mean, you don't see the tachyon. These are long strings, right? This will be really a flux tube. There's no tachyon. There is the massless mode of the long string only, no?
This is an exact result, is it? So it's a. So it's not necessarily a long string, is it? It's R. It's a.
But it's not. But R is fixed. You fix R, right? You put the theory on. You stretch the flux tube. So it's different from computing the spectrum of short strings. It's not the spectrum of short strings.
Yes, Pedro, I agree. Yes. So there is no tachyon here.
Sorry?
So there is indeed, I agree with Pedro. There is no tachyon because the string is long. The tachyon is for infinitely small strings.
Okay, so in one direction it's long. This is what you mean.
Mm.
Even if R
sorry,
is not
I think
long, right?
it is the spectrum of string or of the flat strings.
Yes.
And you could just think of flat strings on some Lightcon gauge, and then R is the charge of some U1 generator on your Lightcon direction, and you sum over all R's, and that's precisely summing over all R is exactly the spectrum that you get from quantization of flat strings, and there is a tachyon because of the CF minus 12 over 12 with the minus sign.
Really?
Put n0 equal n0 bar equals 0, and I think that in general you can have this thing under the square root to be negative. You tune the rest.
Yeah, which is the branch point.
Yeah, precisely.
So you fix even p equals 0. So you drop this, and you take n0 and bar 0 to be 0. So you are looking for the ground state, and then this might become negative for some value. And this is.
Yeah, the transition is exactly when the object under the square root is 0, no?
Yes.
So you go from positive to negative.
Absolutely.
So we need also to have break at some point.
Yeah, is it a good point to have a break, Roberto?
It's I think. Well, I have still many slides, but I'm going slowly.
So when will be the natural point, you think?
Yeah.
Okay, so let's do the.
Yeah, but take it easy, because we are. I think we are understanding, which is the most important fact. Although you have 200 slides, but we don't understand anything, so it's better this way.
Yeah, it's better this way. I agree. Okay, so let's carry on 2 minutes or whatever for the identification. Okay, so I mentioned that you have there is a relation between this Cdd factor and the TTbar operator, And how this comes if you start from the Bourgeois equation written in this way. Now what you can do is identify the energy and momentum in terms of expectation value of a component of the stress energy. A tensor. So En is a T22. So from this point of view, time is the second component. The pressure, so the derivative of the energy with respect to R is a T11 as proportional. And the momentum is T12 times R and this I factor. So you plug this expression here, this identification in the Bourgeois equation, and actually the left-hand side, of course, remain the same. On the right-hand side, actually, you reconstruct the expectation value of the TTbar operator. So this, okay, so this is the definition of the TTbar operators. As essentially, it's related. So this is the alpha of the trace of the stress energy tensor. This is the holomorphic, well, the T and T bar component of the stress energy tensor. And so essentially this is building up the determinant of the stress energy tensor. And the fact that Sasha Zamolodchikov discovered many years ago that this TTbar, the expectation value of this composite operator defined in this way up to total derivative, actually factorize in this simple way for over any state of the theory. So TTbar, which is defined in this way, TTbar minus theta theta, or theta bar, which is the same for the stress energy tensor. If you take the expectation value over any state, then you factorize always in this simple form.
Small comment. You need the translation invariant for this.
You need translation invariant. So this is under very broad assumption, but I think there are still some subtle points that might be might need to be explored. But let's say once you assume this, so this equation, you might think of reconstructing the partition function, which satisfies this relation, and then it essentially means that at a classical level, you can associate to this classical level a flow equation for the Lagrangian. So takes the derivative of the Lagrangian with respect to tau is equal to the determinant of the stress energy tensor at fixed tau. Okay, so this is a flow equation, and actually, and it's a classical equation, or somehow is the classical limit of this equation here, and it allows you to construct, again, it's a first order differential equation in tau, it allows you to reconstruct the full perturbed Lagrangian starting from the unperturbed one. Okay, so maybe this is the right point to stop for what, about 10 minutes, something like that?
Yeah. Okay, thanks. So
okay, I can stay here. So if you have any question.
Okay. Roberto, about the tachyon, I think that both are true. Both statements are true. So if R is larger than the Hagedorn radius, where the square root appears, you have tachyon. If it is smaller, then you don't have.
Okay.
Mm-hmm. Sure,
yeah.
Sure. But yeah, for generic R, you have the threshold.
Yeah, there is a threshold. Yeah, a critical point.
A silly question. Excuse me, Robert. This tau now is the old tau.
Yeah. So at this point, then we have essentially a full match between what we did, including the Cdd factor, and a parameter here perturbing the Lagrangian. So there is an exact match between the, let's say, the discussion, a quantum level using thermodynamic Bethe-Ansatz, etc., and this classical result for the Lagrangian. So you see, at first level, so you start from tau equals 0, okay, and then you continue. You get the first correction. The first correction is essentially this TTbar operator, and you carry on, and everything. It's you know, it's you know, the flow is fully described by this equation.
I see. I see.
So suppose you start from an unperturbed Lagrangian, you can, from this unperturbed Lagrangian, you calculate the stress energy tensor, you take the determinant, you add it to the Lagrangian, you have a new Lagrangian, you calculate the new stress energy tensor, and you carry on in this way, and you build up the full Lagrangian of the theory, at least in this perturbative way. But there are other alternative ways to solve this equation exactly, let's say in a non-perturbative way.
But this equation is meant to be only classical, or you mean also that it's through on brackets of quantization or fluctuation?
Can you? Okay.
Okay. So. Okay, let's say this is a flow equation for the Lagrangian, because once you know the Lagrangian, you know the terminal, it's the stress energy tensor, and you can solve essentially this equation. So if you, so for example, if you start from a bosonic Lagrangian with a generic potential, so this L50 is just this term here, then you can solve the flow equation for the Lagrangian and find the exact form of the Lagrangian, of the perturbed Lagrangian, okay, which contains again a square root, and this B term here, which is this term here, and somehow here you have this coupling constant tau, which is dressed through the potential V. Okay, so if you set V equals 0, and you can say there are a set of n boson, actually this becomes the Nambu-Goto Lagrangian in the static gauge. So everything is fit together. So we have the classical Lagrangian, which for V equals 0 is the Nambu-Goto Lagrangian, and at quantum level we also have the quantum spectrum, which is also fitting the Nambu-Goto spectrum, at least in the critical dimension. Okay, so this Lagrangian is quite complicated. So what we did with Riccardo and Stefano was to try to solve to study, you know, to solve this, the equation of motion, and to study a particular integrable model. So which is again the Sine-Gordon model. This is because we know that if you start from an integrable model, then the TTbar perturbation is not spoiling integrability. So you deform the model in an integrable way. So it's an integrable deformation of an integrable model. So we start then by studying the Sine-Gordon model, and these are the equation of motion out of the Lagrangian or action. You can derive the equation of motion that are in general very complicated. So the square root is hidden in this factor S here. And once you have the equation of motion, what we did try is to construct the Lax pair, and we managed to do that. And so we're ready to calculate conserve charge and things like that in the deformed theory, but at a certain point we actually realized that everything was related to a change of coordinate, a field-dependent change of coordinate. So to explain the point, this so now I'm complex coordinate, so I'm swapping between complex Euclidean and a certain point even in Minkowski. But suppose you have this Jacobian, which is defining the change of variable between the variable z and the variable w in this way. So which is defined in this way. So here on the diagonal, you have the identities minus tau v, which is essentially theta, okay, the alpha, the trace of the stress energy tensor. Here you have t and t-bar, which are multiplied by this factor here. So this is this Jacobian define of change of variable from the variable z to the variable w. And the main claim is that if you want to find a solution of the TTbar perturb equation of motion, then this is equal to a solution of the undeformed equation of motion, so tau equals 0, evaluated in this new coordinate, which I call W, which are field-dependent coordinates. So depend on the solution you are considering, okay? But this is really a map. If you know the undeformed solution, then you, through this change of variables, so you know, for example, also this two component and this two component on the Jacobian, through this change of variable, you can, you get the deformed solution. So the solution of the deformed equation of motion. And actually, if you apply this change of variable to the equation of motion, the form equation of motion, actually they reduce. You have just to look at the nominator here. They reduce to the undeformed equation of motion in the new variable, in the deformed variable. Okay, so this is, there is really a map through a change of variable, field-dependent change of variable, so solution-dependent change of variable. Okay. So this again looks like, let's say, some geometrical meaning, and through this map we were able to, for example, to deform the kink solution in the Sine-Gordon model, which is the solution which is interpolating between two adjacent vacua in the Sine-Gordon potential. So you see this. This is for tau smaller than 0. Okay, so this is for tau greater than 0. You see that the kink solution, the standard kink solution, which is doing something similar to that, is bending in this way. It becomes multi-valued. Is, you know, is branching in this way. So this is essentially the equivalent of the wave breaking phenomena of shock wave phenomena. Okay. But everything is analytic in this in our case, for negative tau, instead the solution is bending the other way, so it's become flatter and flatter for negative tau. So it's bending this way, so become first sharper, and then there is a branching, and in the other direction, negative tau is becoming flatter and flatter. And the same thing happened for the breeder solution. The breeder solution is the bound state of a kink and an anti-kink. It's time dependent, so it's breeding. So this is the time axis, is oscillating. This is the unperturbed solution. For tau negative, this blob is becoming fatter and fatter. And again, the solution, even for tau negative in this case, become multivalued. In the other direction is shrinking this way, and again you see that the solution becomes multivalued. So it's in this case developing branching both for tau positive and tau negative. Okay, so let's go ahead. So this was the case for the Sine-Gordon model. The Jacobian of the transformation was written in this way. And now you can easily generalize it to an arbitrary theory, just replacing this with the theta, half of the trace of the stress energy tensor, and this with the t-bar component of the stress energy tensor in a complex coordinate. Okay, so now it is important that here in this Jacobian there is a conserved current hidden. because if you demand, if you impose the equality of the mixed derivative of the transformation, this here, the consistency, then you discover that this is only valid if here there are the component of some current which is conserved. So in this case, it's a stress energy tensor. So this implies this, and so it means that in the Jacobian, if you really want to invert this map, at least for small tau, then the component, so some conserved current must be hidden in this Jacobian. Now we have a change of variable. You can start from the action, which depend on tau, perform the change of variable inside the action, and actually, this is the change of variable, and what actually you get is the unperturbed Lagrangian in the W variables here, plus the tau TTbar, the TTbar operator, which is the bare TTbar operator. Okay, so this relation here is quite general, and also in case of, for example, of non-relativistic TTbar deformation, you can start, for example, for assuming this, performing the change of variable, and you recover the full Lagrangian, the full deformed Lagrangian. So this is a very powerful observation, and if you assume this, then you can reconstruct many Lagrangian for perturbed Lagrangian. Okay, I can skip this. This is just to say that if you restrict yourself to integrable models, and then you have an infinite number of conserved currents in your system, and you just replace in the Jacobian the component of the stress energy tensor with the component of higher currents. Okay, there are many ways to do that, and so it means that you can enlarge the space of your theory, of integrable theory, with an infinite number of parameters. So you can do this, and then you can also take combination of TS, etc., etc. So it's a huge generalization. So now I move close to the four-dimensional case. So when you have a change of coordinate, you usually think about, you usually associate with a change of metric. Okay, so to set up things in the correct way, we write our object in a covariant form. So, well, G, for example, for the moment, you can think about G as a flat metric. But anyway, let's write it in the covariant form, and I hide this square root of G, where G is the determinant or minor the determinant of the metric inside this L. Okay, so when you write in a covariant form, then this is the Hilbert stress energy tensor, the definition, and then the flow equation for the Lagrangian is acquired this G to the 3/2. And this is, again, the determinant of the stress energy tensor. Now, and this is the original flow equation for the Lagrangian. Now we can write, it's convenient to write the determinant. So this is taken from Cardi approach, but it's similar to other approaches to the TTbar deformation. So now let's take this determinant and write it in this way. Okay, so essentially I'm using this property of the product of the Levi-Civita symbols to write this, to introduce the T tilde tensor, which will really transform again like a tensor, which I write in this way. Okay, so this is an identity. So this determinant here can be written as square root of G divided by 2, T tilde contracted with T. So in this way. Okay, so this is an equality, a rigorous equality between the determinant, so this here, and the introduction of through the introduction of T here and T tilde defined in this way. Okay, now let's take this action here, which is the, let's say, unperturbed action. So the action, the normal action with a small change, infinitesimal change in the tau parameter. So this is, it appears tau plus delta tau in here. And you expand this at first order in tau. So I'm keeping only the first order because really delta tau is infinitesimal. And then this is what you get. Okay. Now you use the flow equation here, and you can write this this term using the determinant in this way. Okay, and then you can write this in terms of t tilde and t. Now let's see how the equation of motion, they change with a little change, a small infinitesimal change in tau. So these are the equation of motion coming out from A prime. So this, you don't have to read this, but they have a standard form. So I'm assuming that there is the field, and the metric here, it's for the moment, you consider it as a flat metric, for example, and is not depending on the field. Okay, so these are the equation of motion. The alternative approach to get the same equation of motion, and this was essentially introduced by Cardi, is to start instead from this action here. So again, it contains the action at tau, so the Lagrangian at tau, plus a small deformation, delta tau, and now you have this auxiliary metric here, or the auxiliary tensor here, h mu rho, written in this way, and then h is coupled to the stress energy tensor in this way. Okay, so this is a standard way. I think it's probably very common to string theorists. Well, it's very similar to Polyakov approach. Now you have this metric here, so this field here, h, which you consider as independent. You calculate the equation of motion, so you have variation with respect to h. Okay, h appear only here, so you get this equation here, which is a relation, which imposes a relation between h and t. Okay. And then you do the variation with respect to the field, so the matter field, and this is what you get. So h would appear here and here, okay? Now, you take the first expression here, and you discover that h is actually equal to this object, which is equal to -2 t tilde, which I introduced before. You use this expression here into here, okay, into here in the second equation of motion here, and actually you get the equation of motion that you first derived through this, okay? So it's the same equation of motion, okay? So the trick is to introduce this auxiliary field here, fix its dynamic essentially in terms of the stress energy tensor, and then plug it in the equation of motion. Okay, so this, if you use this procedure, then this action from this point of view is leading the same equation of motion of the previous action. Okay, so this is the alternative definition of a TTbar perturbation. Is essentially this stage is an infinitesimal redefinition. They are leading to the same equation of motion. So, okay. The second observation, if you look at this, you have a linear term in h, and this t mu nu, which is related to the derivative of the Lagrangian with respect to the metric g mu nu. Okay, so these two bits in the previous action, they can ascend together as a small variation of the metric. Okay. Okay, so the end result is the following. So in this case, in this part here, you have L, which are redefined metric with a small redefinition of the metric depending on this delta tau parameter. And then you have this part here related to the quadratic, you contain the square of h essentially. So it's quadratic in h. Okay. So the idea is that we are now defining a metric essentially on shell that you can use when you describe the equation of motion, you describe the solution. Okay, now you have this metric and you can calculate how the curvature is changing through this metric. And actually, you see this is the scalar curvature is R, and it become equal to, it's a small variation of the curvature, become equal to R0 times, this is the Einstein tensor, 0. So this means, as we expected, because it's a change of, it's, you know, we know that bar is essentially a change of coordinate, that if you start from flat space, then the space remains flat, okay? So essentially it means that the metric, or the small variation of the matrix correspond to, so the metric is equal to the Jacobian, the product of the Jacobian, transpose of Jacobian and Jacobian of the transformation in this way. So it, you know, in this case, in the two-dimensional case, a change of metric can be reabsorbed as a change of coordinate in the equation of motions, so in the solution. So stuff that we know at the full non-perturbative level, because at this stage we are only at an infinitesimal variation of the of tau. Okay, so this is, it's easy to check that the associated Jacobian has the same form as we discovered a non-perturbative level. So, but now this parameter delta tau is infinitesimal. You can describe a flow equation for the Jacobian, which has this form as you vary tau. So if you take derivative of with respect to tau of the Jacobian, and then from this Jacobian you can immediately get the flow equation. So this flow equation, you can get the flow equation for the metric. So the derivative of tau with respect to tau of the metric is actually to t tilde defined as before tau 1. Okay, so this is a flow equation. It's you know, similar to the flow equation for the Lagrangian. It tells you how the metric is flowing with tau. Okay, so the next step is to move from this equation, so from an infinitesimal deformation of the metric to a finite one. So essentially a finite deformation is related to, is the product of an infinite product of an infinitesimal one. And actually what we did essentially is Taylor expansion around tau equals 0, a fixed point. And actually you discover that the metric, so that the series is actually truncate second order. So this is the exact result, okay? And now this variation of tau is finite, so you get tau 1 minus tau 0, tau 1 minus tau 0 squared. So this is related to a square of t, and actually out of this you get the Jacobian we produced before by other means with the delta tau finite, so equal to tau 1 minus tau 0. Okay?
That is a total square, if I'm not mistaken.
Yes, so this is the Jacobian times the transpose of the Jacobian. Okay, but it's you can, yeah, we know from the beginning that the metric we should get was related to a change of variable, a change of coordinates. So it must be the product of the Jacobian times the transpose Jacobian. Okay, and actually So since the Jacobian is linear in tau, on delta tau, then even G is quadratic in delta tau, finite delta tau. Okay, so this is the exact result, is the exact non-perturbative result. Then you can fix tau 0 equals 0. You start from the unperturbed theory and tau 1 equal tau, or vice versa. You can move from the undeformed to undeformed theory, but just by fixing differently tau 1 and tau 0. Okay, so this means that this is in flat matrix, so I consider the matrix starting from the delta. So yeah, I'm in Euclidean space. So let's move to the four-dimensional case. So the analysis is very similar. Maybe I think any good probably string theorists that know that many years ago, at the beginning of last century, people was very puzzled about the presence of point particles and field, electromagnetic field which diverge close to the particle, so become larger and eventually go to infinity on the point particles. Okay, so and this, as you probably well know, that caused the main problem in quantizing electrodynamics, classical, so quantizing Maxwell theory of electrodynamics. And at that time, Bohr and Eiffel, they saw that the problem of quantizing electrodynamics was related to the fact that the field could blow up at infinity. So there is no upper or lower limit in the value of electromagnetic or electro or magnetic fields. So they follow an analogy, the analogy between non-relativistic and relativistic theory. So they said essentially in non-relativistic theory, the Lagrangian is growing like V square, and V is not bounded, so it can be even larger larger than the speed of light. Okay, but in a relativistic theory, this here is replaced by this, and this square root is putting an upper limit in the speed of light, in the speed of a free particle, which is the speed of light. Okay. So this modification tells you that you cannot go beyond the speed of light in this case, because you encounter again the square root, singularity, and blah 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 blah. Okay, so to limit the value of the field, what they did is to change let's say the Lagrangian of Maxwell Lagrangian. This, so I'm not talking about charges and currents, and deform it in this way. Okay, so this is usually called Bohr-Eiffel Lagrangian, and I like to put the M there because we are talking really about a deformation of the Maxwell Lagrangian. So this expression looks very different from this one, or this one, but actually, if you expand this determinant, you find an expression which is similar to this expression here. Okay, and doing so, they manage really to put an upper bound in the electric field of a charge of a point-like particle, because the result they get out of the equation of motion, so the Bohr-Eiffel, so this nonlinear electrodynamics is this one, which has a finite value also for r equals 0. So it's a way of putting a cutoff at close to r equals 0, leaving unchanged the property at large r. So leaving unchanged the large r property. Okay, so this then people, when managed to quantize Maxwell equation, then essentially forgot about this theory. And this was rediscovered more recently related to M theory and D-brane, etc., etc. Okay, now why I'm talking about this? Okay, because in 2018, we discovered with Riccardo, Leonardo, and Stefano that the Born-Infeld Lagrangian actually satisfied, so this, it's a constant factor, is irrelevant, it might be different from the one fixed here. It's the derivative of the Born-Infeld or Maxwell-Born-Infeld Lagrangian with respect to the parameter tau is actually proportional not to the determinant of the stress energy tensor, but to the square root of the stress energy tensor. So apart from the square root, this theory, it behaves very much the same way as the TTbar deformation. So starting from this and thinking about this Cardi approach, we try to generalize, so to write this determinant in terms of a T tilde tensor defined in this way, okay? So we introduce this F here, which is defined in this way. So very similar to the one to the two-dimensional one, and actually this F has a very similar property to the two-dimensional case. And then now you can write this determinant, square root of determinant in this way. So having introduced T tilde here, defined in this way, and T mu nu there. And then this constant here, as I said, is not really relevant, apart the fact that you need to have, if you are thinking about a generic metric, a square root. Okay, so now you follow the same approach as before. From one point of view, you start again from this action. Now you are in 4 dimensions. You take a small variation of the parameter tau. This can be written using the flow equation and in this way. Okay, so L plus this way here, by plus this term here with an infinitesimal variation in tau. So there is this infinitesimal delta tau there. Okay, so this would give you a deformation of the equation of motion of the initial Lagrangian at delta tau equals 0. And I'm not going to write, essentially are the same as very similar to the one I showed you before in the two-dimensional case. But then we can use the alternative definition. So introduce an action here where with this auxiliary field H, which couple again with the stress energy tensor in the same way, okay? And again, this part here, since T, the stress energy tensor, is related to the derivative of L with respect to the metric, they can be reabsorbed in a change, in a small change, infinitesimal change of the metric G. Okay. Now you calculate again the equation of motion. For example, for H, from the one for H, you get a constraint between a relation, a simple relation that it's identical to the one I described for the two-dimensional case, apart from a factor 2. So H is equal minus T tilde, where T tilde is defined in this way and can be written in terms of the original stress energy tensor. So original in the sense not without tilde in this way. So there is they differ by a sign, okay, and the trace of the stress energy tensor. So, for example, in Maxwell equation, if this was the stress energy of the Maxwell theory, this would be 0, and T tilde and T would just differ by a sign. Okay. Now, as I said, the one part one of the extra part I introduced can be reabsorbed in the metric, in a change of metric, and the procedure is always that this action here would give you the same equation of motion of the other action. So I always have to work at the level of equation of motion. So the matrix always calculated on shell somehow. Okay, now you do again infinitesimal perturbation, and you calculate an infinitesimal variation of the Einstein tensor. And now you discover that it actually is non-zero in general. So if you start, so this is enough, I mean, to say that if you start, even if you start from flat space, then with this perturbation, you move in non-flat space, okay? Okay, so it means that it cannot be, you cannot obtain Maxwell-Bohr-Infeld just by a change of variable from the equation of motion of Maxwell of Maxwell theory. So this is the main difference between the 4-dimensional case and the 2-dimensional case. And yeah, so at this stage, you notice that I'm talking about a general theory, the form in this way, okay? So now, okay, now you can again derive the flow equation for the metric, and it's very similar to the 2-dimensional case. And then you can try to solve this again doing perturbative Taylor expansion at tau around a fixed point, let's say tau 0. And actually what you discover is that the sum, so you have an infinite number of terms and there is no in general truncation. So it's a non-trivial flow that changed the metric, non-trivially. But still, in principle, you can solve this equation at all order in perturbation theory. Okay, but as I say, the final part is very general, but Bohr-Infeld from this point of view is actually very special. And you can prove that the metric, the perturbative expansion of the metric, the Taylor expansion around tau 0 is actually truncating at first order. So it's the calculation of first order is actually exact. So it's even better than the 2-dimensional case. And actually this is the result for the form metric. So it contains again T tilde there. And this is now, it's a finite variation of the tau parameter. So you can fix tau 0 0, and this to tau, and you move from the undeformed. So from Maxwell equation to, for maybe vice versa, it's written here. So if you set tau equals 0 and tau 1 equal to tau, then this is what you get. So you get G mu nu is actually equal to delta minus tau t. This is t, because in this case, the trace of the Maxwell stress energy tensor is 0. So t and t tilde just differ by a sign. And so this means that in this way, we prove the Maxwell-Bohr-Infeld theory with this metric here as the same equation of motion of Maxwell theory in flat space. So you have a Maxwell-Bohr-Infeld theory or Bohr-Infeld theory in curved space, and it has the same equation of motion of Maxwell theory in flat space. And vice versa, if you set tau 0 equal tau and tau 1 equals 0, you get this. And in this case, you have that the equation of motion of Maxwell-Bohr-Infeld associated to Maxwell-Bohr-Infeld in flat space, as it is usual, the standard definition of Maxwell-Bohr-Infeld, are equal to Maxwell equation in this non-trivial metric.
Roberto, can you remind me what is which one is in the standard coordinates and which one is in the other one?
Okay, so in this case, it's a metric chain. is not a change of variable, but is a change, a flow in the metric.
No, but I mean the definition of T. This is T in the original.
What do you mean?
What is the difference between T and T tilde in these two equations?
Okay. So it's the standard definition I gave before is this, essentially is this one. T tilde.
Okay. Okay, sorry.
Okay. So it's a standard.
Okay.
Well-defined map between T and T tilde through this f function I introduced. Okay, so I managed to finish the talk then.
Oh, okay. Okay, thank you very much. So let's unmute and thank Roberto. Thanks for the nice talk. And yeah, please, if there are questions.
Can I ask a question, Roberto? So if I start with a asymptotically flat space with the fields decaying at infinity, is it true that I can interpret that after this deformation, it's still asymptotically flat? Because even though I'm deforming, if the fields would vanish, I still have asymptotically flat.
Yes.
So can I define therefore scattering amplitudes in even before and after deformation? And do they have some? Is there some simple deformation as in 2D?
Okay, that I don't know. I mean, this is the result we had. So, I mean.
Or let me ask differently. So in 2D, is it true that we get this non-trivial S matrix? But for example, from the flux tube point of view, the interpretation is because we change observer, right? From co-moving to static observer.
Exactly.
So is the...
But that's the two-dimensional case. In this case, it's really a flow in the metric.
Right. So, okay, so normally we are used to S matrices are physical observables, they are independent of filter definitions and so on, right? Unless the filter definitions are very non-trivial, right?
Yes.
So we can think that a little bit in 2 dimensions, that's one example, right? Where the filter definition is very significant because we are really changing the frame of the observer, right? So really, even though it's a filter definition, in a way, it does change the S matrix and you get a Cdd.
Yes.
So can you do some perturbative computation or something in higher dimensions and see, is there something happening to the S matrices, to the amplitudes, the 3-level amplitudes of these theories?
Well, you mean something getting some result at classical level?
Yeah, for example.
Yes, I see. You can do this this type of calculation. I think you can do that and see that it matches the S matrix, the full S matrix, so which is consistent with the full S matrix. I think you can do that.
Okay.
And actually,
another unrelated question. Do you have any comments on the relation between what you just said and, for example, the work of João Caetano and Leonardo Castelli and on this TTbar proposal for deforming n = 4? Or?
No, because I think they are somehow at this stage we are dealing with a simple equation. I mean, simple between inverse comma. This is a Bohr-Infeld equation. I think they are talking about n = 4, and so much more complicated. So this is what I know, and it's not. It's probably very far from what they are describing. Might be, related, but it's really beyond my understanding.
May I make a comment on that?
Yes.
On the side of n = 4, I don't have much to say, but if you believe that this TTbar deformation should give you an integrable S matrix, which is deformed by a phase with respect to the Beiser test matrix, then you can try to construct this deformation on the worldsheet of ADS5. So you can try to say, what is the geometry different from ADS5 cross S5? That gives me an S matrix, which is not the usual one, but comes with a prefactor of the TTbar form. And that is a TST deformation of ADS5 cross S5. It's a very simple deformation, where you just do a TST on the time direction and on the other light cone direction that you would use in light cone gauge, basically. So that's that was work with Stein van Tongeren.
But sorry, TST is what is essentially like a twist, right?
Well, it's a twist, a shift, and sorry, the duality, a shift, and a twist, and the duality. And it appears as a twist of the boundary conditions, but basically that's what this prefactor that you have, right? It's just a global phase of the form e to the I and the antisymmetric combination of two charges. That's why, yeah.
But it will be like a momentum dependent change, right?
It is it depends on the momentum and on the energy. So these two charges are precisely the momentum and the energy because they are the light cone directions. And well, in a way that is explained in the paper, you can relate them to worship momentum and energy.
But that's a bit different, like right? That's more in the spirit of understanding how to deform two-dimensional theories without Lorentz invariance. Whereas what I was asking was about deformation of four-dimensional theory, right?
Yeah. So as to what, for instance, whether you can construct a deformation of a deformed Lagrangian of n equal 4, that doesn't answer it. It only tells you what the dual is. Yeah.
No, but it's not obvious that TTbar, four-dimensional TTbar deformation of n equals 4, that it would have anything to do with TTbar deformation on the world sheet of a priori. It's two different things, right? I mean, it doesn't tell you about the dual. It's different.
But then one would have to do with integrability and another is not necessary, right? If you do TTbar in four-dimensional then it will probably ruin.
Yes. TTbar in four-dimensions could break.
Maybe a related comment is that
it's like another set fuck integrability, right? Oh, maybe I should.
Yes.
I did not get what you said, Colin.
That's good. I won't need to edit it.
Roberto, please go on.
Okay, so I have a small comment. It's that TTbar and Maxwell and Bohr-Infeld, they are not totally unrelated because, the metric is essentially its own shell. So you can find a solution of the equation of motion which have particular symmetries. And in that case, actually, you can map Maxwell-Bohr-Infeld equation of motion into two-dimensional, it's a Nambu-Goto theory with only two fields. And this is the two-photon solution, which was described many years ago, again, at the beginning of last century, to plane wave, scattering. And that is an exact map between this some solution of Maxwell-Bohr-Infeld as essentially string theory and TTbar, therefore, in two dimensions. So there are special solutions of this theory that can be mapped to TTbar perturbation. It's essentially you do some dimensional reduction, but you end up in that model. So they are not completely unrelated. So this is probably the reason why this Bohr-Infeld is so similar to the TTbar two-dimensional deformation.
By the way, can I ask a very basic question? It's more about it's not about your talk, but since you are studying all these CDDs, is it true that the original CDD paper was not about two dimensions? Is it true? Do you know the original CDD paper, and can you say a few words about it?
No, yeah.
It's by Dyson and others, right? And I thought it was not even about two dimensions, right?
No, I think I'm afraid it was an high energy physics paper. So like Watson relation, it was on on 3 and 4 dimensions, so 3 plus 1 dimensions, as far as I remember. But this goes back to, you know, to very young studies. Yeah, is Dyson, Davids,
how could they
Castello.
How could they do something in higher dimensions, and now we are struggling so much?
But also Watson. I'm afraid Watson equation was born, no? You know that, Pedro, no? That it was born in high energy physics, again, I think in 3 plus 1 dimension as a property of the S matrix. They were working on S matrix very much on more realistic dimension than what we have. Except Roberto, that now has a window on 4 dimensions. Lucky him.
No, that's okay. Well, yeah. So how could they deform S matrices in a simple way with a CDD? It's probably they were just doing some partial wave decomposition and looking at the lost waves. So then in practice, it was like,
I remember something like this. Yes.
Then in practice, it was like 1 dimensions, probably.
Yeah, like in the book by on the S matrix, no? The analytic S matrix. Yeah, exactly. Partial wave decomposition, this kind of.
So probably it was not really rigorous. It was probably not crossing symmetric, right? You would deform in partial waves, deform each of them, then you spoil completely cross invariants and so on. But yeah, it would be nice to review that paper at some point.
All right, more questions to Roberto, or we like
maybe one which maybe I missed it, but so in 2 dimensions there are all sorts of nice properties for TTbar, and one of them is that you have this nice deforming operator, which is actually well defined as a composite operator. So do you have anything to say on these with regard to this for 4 dimensions?
No, this is all classical. So we don't know. I mean, it would be nice to quantize this theory, but I think they tried for 70 years or more to turn out that it's more problematic to quantize this theory than, of course, standard electrodynamics. So the hope really was to give a limit, so a bound on the field, so that this theory would be simpler to quantize than so would avoid the infinity problem at quantum level. But indeed, they never managed. Nobody really managed to quantize this. So it doesn't mean it's a no-go theorem, but
sure.
Okay, thanks. Are there any more questions for Roberto? If not, then let's thank Roberto again.
Thank you.
Thank you.
Yeah, we can switch time.
Thank you.
Next time.
Oh, next time we have Tristan. So if Tristan McLaughlin, if he is here, maybe he can tell us something about his